I thought today I would start with some basics on sleep and particularly slow waves, since we're trying to understand how to manipulate or enhance slow waves to make sleep better. And Megan has agreed to review the Marshall study, a 2006, I think, study, that we're going to replicate as the first thing to do in the lab. All right. So I'm going to talk just a little bit about the background of sleep and really emphasize neural development, kind of the neurophysiology of sleep. And neural development is a general model for understanding cognition. So there's some theory I'll work into the background. But then look at sleep as a mechanism not only of neural development and the neurophysiology of the developing brain, but also the cognition that Von Leeuw and I have organized or have argued is really part of the ongoing process of neural development. And then I'll focus particularly on the slow waves of sleep, one of the stages of sleep that seems to be important to memory consolidation, or at least certain aspects of memory consolidation that we don't understand. So sleep is well conserved in brain evolution. It seems to be important in ways that we're still trying to understand, but as various creatures evolved, their sleep changed, but they still required sleep. So reptiles have a very unique pattern of sleep with big, sharp discharges that occur, but they have quiescent periods that look a lot like sleep. Mammals got new brain waves and features, including a strongly developed REM sleep, and birds may have a similar parallel to REM sleep. So each stage of evolution seems to have changed some of the aspects of sleep, but didn't eliminate them and the need for it. And we see the same thing in human development. We see in the behavior of the fetus different periods of activity and quiet, and including different brain waves, unique brain waves that can be observed. Some of our colleagues at Columbia University did research with baboons. They took fetal baboons, took them out of the womb, put brainwave electrodes on them, and then put them back in the womb and brought them to term. So they could measure the fetal brain waves as the baboons were developing. And they were quite remarkable in showing these activity periods, but also the stages of sleep with big burst suppression patterns, a big burst of activity and then suppressed activity, almost like the reptilian sleep. And then at 40 weeks, when the fetus is ready to be born, the pattern changes into a much more waking or adult-like sleep pattern that the infant has. So it's a remarkable transition right at 40 weeks. And if you look at preemies that are born, let's say, at 30 weeks or 35 weeks, their pattern is not the mature infant pattern of sleep. It's a very elementary fetal-like pattern of sleep. And it stays there until they get to 40 weeks. And then they kind of wake up and are much more responsive, but they're also showing more mature sleep patterns. So it's very critical to neural development to have the sleep stages. And it never goes away. We always need sleep, even as we get old. The sleep remains some kind of an essential organizing process. And now the question is, how does this relate to cognition on a daily basis? And the answer I'm going to propose, at least briefly, is that cognition and our psychological function is an extension of neural development. That development is not one thing and psychology is another thing. They're the same thing. that the plasticity of the brain, as it organizes connections and builds the connectional architecture, is the same thing that happens when you think or when you feel. All the psychological processes are processes of neural development, processes of ongoing cognition. That's the theory that Fawn and I developed a number of years ago, which nobody believes, actually, except Fawn and I. We have not found anybody else that would accept this theory. We have a lot of very famous psychologists and neuroscience scientists who think this is totally ridiculous. But our argument is this is one theory that you can have about growth and development and psychology. You don't need separate theories for those. They work in the same way. And so really this is the way we approach sleep, is to understand it in this kind of unified aspect of neural development. And one thing that is clear is that sleep engages all of the evolved levels of the neural hierarchy. So just as we looked at the evolution of mesencephalic, diencephalic, telencephalic levels of organization over vertebrate evolution, the embryo organizes itself through those same levels, and all of these levels have a unique role in sleep. And my hope is that over our next seminars, we'll dig into different levels of sleep as we're trying to understand the functional role. But already this diagram illustrates that, for example, the brainstem, a critical structure for arousal and activity control, has its unique role in sleep, particularly in REM sleep, rapid eye movement sleep, and the cycling that occurs between REM and non-REM sleep. The diencephalic level, the thalamus and hypothalamus, has key roles. The hypothalamus maybe is the master regulator of arousal states. Even though it has to recruit the brainstem to do it, it has a balance between a sleep-wake cycle that's controlled by nuclei in the hypothalamus and unique neuromodulators. But the closely related thalamus is also critical to regulating the arousal state and the sleep states of the entire cerebral hemispheres and the cortex. So, and then in turn, the cortex is the controller of the hypothalamic and brainstem regions. So it exerts influences across the hierarchy to organize itself and the entire brain. So there are multiple circuits involved here, and the EEG gives us a clue into them. And we think the EEG will give us a clue how to manipulate the brain states in order to improve sleep. And our project that we have right now, the main funding is for closed loop neuromodulation. So it's a technical project on this SBIR to improve the technology for measuring brain activity and using that measurement to turn around and manipulate brain activity. But the specific application is sleep. We're going to try to measure the slow waves of sleep, and when we detect them, we're going to apply electricity to the brain to enhance it or to synchronize the function of sleep and to make that slow wave sleep stronger and deeper for the period of time. And as Megan reviews this work, there's evidence that it can actually not only make your slow wave sleep stronger, but help you to remember the next day. Now, how does sleep relate to memory? This is going to be an ongoing issue that we want to understand over a period of time, as well as use it opportunistically to try to improve sleep for people who may have sleep problems, but also to improve memory, to try to help people think better and function more clearly. So what are slow waves? So if we go back to the picture here of stages of sleep, you see in this hypnogram that Eustace created with his machine learning detection of sleep stages, you see the cycles of sleep. So you start awake and you drop through into early sleep, the first stage, N1, and then a little bit deeper stage, N2, where spindles start appearing and K complexes. And then you get into slow wave sleep that we think of as the deepest stage of sleep, N3 or N3 and N4 in the old nomenclature. And so there's a lot of pressure to get into that deep sleep. So if you stay up late or stay up all night, there's pressure to go into that slow wave sleep. And as soon as you do, it relieves. And you no longer have that homeostatic regulation to go to deep sleep. But there's also a cycling that happens that you can kind of see here. After the deep sleep, you pop back up to REM. There's not much in this little episode. But you cycle back down and then back to REM in a cycle of about 90 minutes during the night. And increasingly, the REM gets stronger and the slow wave gets less strong over the course of the night. And there's evidence that that 90-minute cycle happens all day. It happens all the time, that even as you're going through your activities, you have a cycle in which you're more likely to fall asleep or even maybe have fantasies and REM-like cognition on a regular cycle during the day. So the question is, what do each of these stages do for memory and how do they organize it? And we're going to start by looking at the deep sleep, the slow wave sleep, and what are these slow waves? When they're only characterized with a couple of channels, a couple of recording sites, we really can't map them very well in the brain. We really don't know where they come from. And the mapping to different brain structures might be important to understanding their function. So we're particularly interested in work in Massimini and Associates in the Tononi lab at the University of Wisconsin, where they took the dense array EEG, 256 channel EEG, as people were sleeping and did some of the first carefully organized dense array EEG studies of sleep. And what they found is illustrated here in this plot. The big circles show the onset of waves, where they were most likely to begin, and then the lines show the connection of them. So what they found was the slow waves of sleep are not everywhere. They're not global. They have a specific topography or patterning. And in fact, they start in the front, the frontal areas. And then they seem to propagate down the midline toward the back of the brain. So why is this? Why does the frontal lobe engage these slow waves? There's quite a bit of animal work that suggests that the slow waves involve the hippocampus and an interaction between the hippocampus, kind of a core primitive area of cortex, and the rest of the cortex, but also the thalamus. And there's a circuit involving these three different structures that seems to be important in memory consolidation. So being able to see the frontal lobe and its role might give us an idea of the cortex's control or integration of these sleep cycles. And just briefly, we'll probably try to go into this at a later point. The idea is that during the day, your hippocampus and some of its associated limbic cortex are helping to hold on to new memories in a kind of a volatile state. And then when you go to sleep, they're reading out those memories back to your cortex so that the next day, now your cortex has them instantiated or held on to. So that's the idea of consolidation. The limbic structures are active in the early plastic stages, and they interact with the cortex to hold on to memory. Now, we think that's going on all the time. So as you're listening to what I'm saying, there is an interaction between your limbic structures and your neocortex, I hope. And I hope it helps you to hold on to the memory. But the evidence suggests that you'll hold on to it best if you have a good night's sleep. And that's part of the consolidation process. So one of our goals will be to map the slow waves. And one of our questions has been, well, how can we manipulate these slow waves to make them better? Well, we should know where they're coming from in order to provide that manipulation. And now this leads us into kind of an interesting scientific problem and quandary of where do the slow waves come from. So here we modeled the frontal lobe as generators, but we also modeled the temporal lobe. So this is with our geosource software. We can make a part of the brain active and make it a dipolar source. And then we can look at the field that would happen on the surface. So a brain part is active. It has positive and negative fields. Each part of brain is dipolar. It has a positive part and a negative part. And then with this modeling, we can see where it goes and where it maps. And part of what we saw in this activity is that the frontal generators are pretty tight. And the temporal lobe generator is pretty tight too, compared to the patterns that we saw in this work. For example, here's one right here. Now, if you look at this field distribution, part of what we'll be studying as we analyze the EEG is how to read the field pattern across the whole head and understand the possible sources that could generate it. That's really the task of relating the brain waves, the electrical field, to the brain and its generator. And there are really physics of the dipoles and how they generate the field. And we'll have that be part of our Bell training over time. But part of what we learned with that, if you look at this pattern here, it's not just that the wave has a big positivity up here, it has big negativity all around the inferior area. And the way that would come about actually is not from a frontal generator, but from temporal lobe generators. And the reason is, in order to have a big negativity around the bottom of the head, as well as a positivity up here, the source has to be right in the middle between those. That's the nature of a dipolar field. So the interpretation of this research, as we've gone on to do our own modeling, doesn't seem to work, actually. It seems to be that somehow, even though they were using EGI equipment and software, their interpretations didn't seem to work. So I remembered something that these guys had said, that they didn't like the electrodes around the neck. And so they took them out and ignored them. And that might be problematic because what we find in some of our own mapping studies is that even though the frontal brain is generating important parts of the field, actually you have to look at the whole picture. And we just started looking at some of our new recordings in the lab that we did in our first sleep studies. And we're looking at the slow waves. And so Evan and Megan have been marking these, and we're looking at where they happen. And sure enough, there are big inversions of the slow waves around the back of the head, and not just the positivity that looks so striking up in the front. So I went back in kind of preparing this talk and looked at some of our studies of frontal discharges related to slow waves in epilepsy. And one of the interesting things is that there are seizures called spike wave seizures, and they occur about 2.5 cycles per second when they happen. And they're also called generalized seizures or generalized epilepsy. And they're very interesting. They occur most often in girls, although almost the same frequency in boys, not quite. And they often go away in development. and so often they won't even be treated. They're called absence epilepsy. It used to be called petit mal or petit mal epilepsy. And it's a very interesting process if you see it clinically. These seizures cause the kid to lose their attention for what's happening. In fact, they space out, but they don't fall down, and they're not convulsing. They just space out for 30 seconds, and then they're right back with it. And the interesting thing is, psychologically, they don't lose their orientation to what's happening. Now, the reason that's interesting is that anything that makes you unconscious makes you disoriented. So if you get hit in the head and you're unconscious, when you wake up, you don't know what's happening. You don't know where you are and what happened. If you drink too much and pass out, same thing happens. It wipes your memory for that period of time. But these seizures cause you to lose consciousness, but not lose ongoing memory. So it's a very interesting process to understand the implications. But as we map the activity, there are two things I want to emphasize. One, these seizures often occur right out of slow waves in sleep. And this is something we published in 2009, and you can see the effect right here. So here's this patient is asleep. There are spindles and slow waves. So you can see that we're up at the frontal pole. FP1 is the frontal pole. And there are pretty big slow waves that are coming out in looks like a normal sleep pattern. And we have 1, 2, 3, and then pop, this big nasty discharge that goes into a complete seizure. And it's a spike wave seizure. You can see the wave and the spike, and they are at 2.5 cycles per second, very characteristic of this generalized slow wave spike seizures. So the implication is the mechanism, and we've seen this in a number of cases, that the mechanisms of slow wave sleep involving the hippocampus, thalamus, and the frontal pole are the same mechanisms that get pathological in these seizures. And they have really interesting similar features. Now, what does it mean about consciousness that we have to have this slow wave period as a part of our natural physiology, but that if something like it occurs in a pathological cycling during the day, we lose consciousness, but we don't lose memory? It's a very interesting neurophysiology of the fractionation. But even going beyond the basic questions, we have interesting questions of the physics that generate the field. So here's another case of the spike wave seizures. Now this is not during sleep, this is during waking, an earlier study. And you can see here, this person is moving along with a pretty normal EEG. There's an abrupt little spike and wave here that doesn't look so good. But they're awake, alert, and then all of a sudden these big discharges happen. And this is the absence period. So when this happens, the person cannot respond. If you talk to them, it's like they're not there. They just stare ahead. But they don't fall down, they don't have convulsions. And when you talk to them afterwards, they know where they are. In fact, they can even remember what you were saying before they started seizing. So the brain is there, unlike anything else, but it's kind of not with it. This critical core mechanism of consciousness gets disrupted. So when we map this, we see something that's similar to slow waves and very relevant. And in fact, this will be guiding some of our analyses that we'll be doing with slow waves and sleep. And I think the conclusions will be somewhat different from what is published earlier. And I can emphasize that in just kind of a brief analysis. So if you see this discharge up here, it looks like it's mostly up in the frontal area, but see how it's inverting all around the back of the head? Particularly not the spikes. The spikes are pretty localized to the frontal pole, the Brodmann area 10, a uniquely human area of the neocortex. Even apes don't have much of a BA10. It's the thing that sets us apart. That's where the spikes engage. But the wave, this big slow wave, is inverting over the back of the head. See that kind of wavy picture that goes back there? And if we map it and do maps over each period of time, we can see the big wave up here that peaks at 168 milliseconds after the beginning. You see a pattern, but it's as positive in the back as it is negative up in the front. That would tell us the generators are in the temporal lobes. Compared to the clear peak at 224, a positive going peak, and then an inversion at 240, the negative going peak. So here at 224, you see that positive peak up at the pole. It moves along and then flips into a negative peak up there. Both of those are clearly frontal polar generated. And here's a map of them. Here's the slow wave at 168. And that slow wave is not in the frontal lobe. It is clearly temporal lobe as a generator. Whereas the spikes are frontal polar, and we can separate those and delineate them. Now, there's some complex neurophysiology this implies about the frontal lobe and its projections to the thalamus that regulate the thalamocortical projection. There's a circuitry of the thalamus and the neocortex that we have to understand. But the main implication is the slow waves of sleep may not be just frontal lobe. They may involve temporal lobe and maybe even hippocampal territories that are engaging the memory process as part of consolidation. So as you can see, this is very exciting. This is a chance for new insight into neurophysiology that we can explore with as we bring our tools of EEG to understanding sleep. All right, so I'm going to stop there and entertain questions here before we go on to look at the specifics of the study that we're going to replicate, and Megan will walk us through that. Yes?
So the EEG from the seizures that you've shown in this presentation,
Yep.
is that pretty typical of like all types of seizures, or is that just a very specific?
This is only for absence seizures, only for the petit mal seizures, and they're pretty unusual. And like I said, they're developmental. They happen to kids. And maybe a third or so of people, they don't outgrow it, and they still have it as adults, and it becomes chronic. But it's a unique type of epilepsy. Now, the neurologists call it generalized epilepsy, as if it happens everywhere all at once. And that's just bad neurophysiology. It clearly doesn't. It happens in the frontal pole where the spikes are, and the slow waves are broad. But I'm pretty clear that they're temporal lobe from our own mapping of it. So it's a kind of epilepsy. The frontal thalamic circuits seem to become pathological in development. An interesting thing is these absence seizures are unique to humans, and maybe baboons, actually. There have been reported in baboons, but no other creatures have them. So maybe it's our evolution of the frontal pole that makes us unique, that cause during development to be somewhat in transition. But other seizures are not like this. Other seizures will engage other cortical areas, and they almost invariably will engage the limbic structures, the amygdala particularly, and the hippocampus at the core of the brain. And then when those seizures happen, your memory is wiped out for the last period of time. And the more severe the seizure, the more severe your memory is. So there's something about ongoing memory that's critical to consciousness, but there's something else about the frontal thalamic regulation of alertness and voluntary control that's a separate function of consciousness. And in fact, we even wrote a paper about this. in which we said that these seizures can tell us that consciousness is not one thing, it's two. That it has fractures between this frontal thalamic regulation of intentionality and will versus the limbic regulation of ongoing memory for who you are and what's happening. So there are other lectures on consciousness this week. Christoph Koch will give one at 2 o'clock on Friday. Stan DeHaan will give one at 4 o'clock on Friday. But I'm just preparing you. They're going to tell you there's one thing in consciousness, and it's not. It's at least two. Yes?
So in the absence seizures, are they, you said that they're aware of what's happening? Are they aware
Not so much.
Seizure?
No, they're not aware of what's happening, but they don't forget what just happened. That's the so while they're seizing, they're not tracking ongoing things, but they remember where they were just at a few seconds before, and often it's only 30 seconds of the seizure or even less. And so they're reoriented as soon as they come back. Some kids will be writing, they'll space out during the seizure and they continue their sentence.
So they're not aware that the time has passed then? Or
That's correct. They're not aware during that interval. If you try to talk to them, they don't know what's happening. They can't respond.
How do you know that it's a seizure as opposed to just a kid spacing out? I mean, going into daydreaming or something else?
Well, it could be that. And when you're sitting with the kid, you don't know the difference unless you're recording their EEG. And in fact, what you see then during that spaced out period is this big set of discharges. And I've done this with the patients. When you're sitting with them, it looks like they just space out. They're, nothing's really happening, except that they can't respond to you, and their brain has these giant seizure discharges.
And if you don't see those discharges, but they're spaced out, then they must be just thinking of something else?
Yes, that's right. That's right. And kids will space out. They go in and out half the time. And, college students do the same.
Just like that.
Yes, exactly. Exactly. No, college students do the same thing, particularly during lectures. You'll get to the really good part, and they have this kind of totally vacant look on their face. But, I've often wanted to see EEG. What's going on with that kid? But, yeah, and without the EEG, you can't discriminate it.
So somebody that is just thinking of something else while you're talking to them wouldn't see those spikes?
That's correct. That's correct. This is a seizure, a very definite thing.
So how common do you think this actually is? Because it seems like it would go undetected unless a specialist examined them.
Well, yes and no. They are non-functional during that period. And so an alert teacher will know this is not just a normal space out. This is an unusual thing. I had a good friend, actually. The first time I learned about absence seizures was I had a friend that I was rock climbing with. And we were doing an overhang, and he just let go. And he was really a good climber, and I had no idea why he did that. Now, I had him on belay, and I was able to catch him, but it was pretty scary when somebody just drops. And then a couple of weeks later, he was driving, and it wasn't with me, it was somebody else, and he just drove off the road. We eventually found out he had absence seizures during that. So the person is not functional, and it's actually very dangerous for driving or other things when it happens.
Oh, I was just going to say, I've taken a class with Professor Nikki Swan over at
yeah.
Oregon,
Yeah.
and she talks about absence seizures, and that a lot of times it does go misdiagnosed, since a lot of parents just think that their children are spacing out,
Right.
and it's not until it happens very, they start to see it more often that they decide to take precaution and go to the doctor.
That's right.
Mm-hmm.
And it can be difficult to
Yeah.
know what's happening with different kids.
Yeah, definitely.
You have to, and the EEG will tell you, but it's not so easy to put an EEG in a kid in the classroom. And even when you bring him into the lab, you know, they may not have the seizure right then. It doesn't happen all the time. It can be very infrequent.
You said that it was developmental, right? Like, do they grow out of it, or is it something that you have to treat?
It depends. Usually, often they will grow out of it. It should be treated though, and there are certain anti-epileptic drugs that are effective, particularly with absence. So it should be treated if it's noticed, and it may help the kid function. Yep.
Have there been studies showing like the difference in their sleep? If they're having like these slow waves during the day, do they have less slow waves at night?
Good question. That's a very interesting question. There is one syndrome called status epilepticus of sleep where they have these spike wave seizures as soon as they fall asleep. Now, we showed that one patient who had his slow waves, normal slow waves of sleep, and then popped into the spike wave seizures. Apparently, this is pretty frequent, particularly for children, that they will go into this. And parents often don't notice it. I mean, they just have this little seizure discharge as they fall asleep. It's probably not good for their brains, but then some kids get stuck in the seizure, and it just goes on for minutes and hours. So there are very close relationships between the normal control of sleep, particularly slow wave, and the seizure process. And it is clinically important for children. But it's not very well understood. It's something that would be really interesting to study. All right, I'm going to quit now and let Megan tell us a little bit about the study that we're going to try to replicate. Because our goal really is to understand what's been done before and then how we could use our technology to try to consistently improve slow wave sleep with transcranial electrical stimulation.
Okay, so this paper is called Boosting Slow Oscillations During Sleep Potentiates Memory. It was a 2006 study by Marshall et al. And that's what we're going to base our study in part on. So the participants, we had a total of 13, 7 female. The age range was 20 to 28. The participants were not on medication, they were non-smokers, and they excluded for epilepsy paroxysms, which is some kind of fit that was in the paper, and cognitive impairments and any sort of disorders, mental, hormonal, metabolic, or circulatory, or sleep disturbances. So they're all healthy people. And the overview of the procedure, so they had a night of sleep in the lab for habituation, and it was unclear from the paper whether they had a habituation night before each experimental session. So I'm not sure, but there was 2 experimental sessions. They had a stimulation session and a sham stimulation session for sleep, and they both included learning, procedural and declarative learning and testing. And the stimulation and sham sessions were separated by at least 1 week. I thought that was interesting. So the procedure for the experiments, they would arrive at the lab at 7 p.m., get set up for the neuromodulation or sham, and they had a learning period. They did procedural and declarative learning tasks, lights out at 11, and then they would sleep for about 7.5 hours, and they would either get the stimulation or sham. And then recall testing was about half an hour after they woke up. So they're learning up until about a half hour before they go to sleep, and then they're being tested about a half hour after they wake up. So the stimulation location, electrodes they chose were F3 and F4. And so that was where the positive current was, and then the mastoids was the cathodal. And they didn't say whether it was to the ipsilateral or contralateral mastoid, so I'm not sure about that. Electrodes were 8 millimeters in diameter. The current was oscillating frequency of 0.75 hertz. So there's some research that shows that the frequency peaks between 0.7 and 0.8 hertz, and so they picked what was right in between that to enhance the slow wave. So the oscillation was 0.33 seconds on, 0.33 seconds off, and the maximum current density, I don't really understand what that number means, but I thought that was important for people who need the technical information from this paper.
Yeah, that's really the current you put across the square area of the electrode, or the surface area of the electrode. So higher current density is the same amount of current over a smaller area or more current. Yeah.
Okay.
And that, it determines how much it hurts, basically. If your current density gets too high, it hurts.
And they said that they did pilot experiments that showed that you couldn't feel the stimulation, which is what is pretty standard for ours too, so. So the stimulation began after 4 minutes of the first N2, so that's the non-REM stage 2 sleep. So they had 8 consecutive 30-second cycles of sleep scoring that determined that they were stable in that stage of sleep. And so the current was applied over 30 minutes, and that would be 5 minutes on, 1 minute off for 5 cycles. So that totals out to 30 minutes.
So what's interesting here is they're not in slow wave sleep when they started. They're in stage 2 sleep, not stage 3 or slow wave. But they're kind of expecting that they've been in it long enough that they would be ready to go into slow wave sleep.
Yeah, exactly. And the paper that they did in 2004, this group of researchers, they induced the current in slow wave sleep. And then for this study, they did it where they think it's going to progress to slow wave sleep, but before they actually reach slow wave sleep. So then this is the time course of the experiment. So it's kind of hard to see, but those red bars are the 5 minutes off, or 5 minutes on, 1 minute off stimulation cycles. And so you can see the hypnogram of the sleep stages sort of underneath the red bars there that shows that they are pretty much after the first 5 minute block, they are starting to drop down into the slow wave sleep. And in this experiment, they separated out stage 3 and 4. I guess that's not the current way that they describe it now. It's just all slow wave sleep, 3 and 4 are combined. But for this paper, they showed it as 2 separate stages. And so you can see that they do go back up into stage 2 after a few of the stimulation intervals. And then they just progress through their sleep as normal. And so the gray bar in this picture is, that's the lights off period, and then you can see they have learning pre-sleep and then recall post-sleep. Right. This is just some technical information about the EEG. So they used a Taiwanese DC-AC amplifier. The filter was between 0.8 and 35 hertz, and they sampled at 200 hertz. I think ours were sampling at 250.
Yeah,
right?
typically, yeah.
And then they used FZPZ, FZCZPZ, et cetera. You can read all the numbers there, and they reference to the nose. I haven't heard of that before, but
Yeah, it's one of the references that people use. Auditory researchers like it because the temporal lobes are pointed in such a way that the auditory potentials have a zero line that's around the nose. So if you want your reference to be zero, which is kind of a dumb thing, but the nose would be a good choice.
okay, yeah, so we're obviously gonna do that a little bit differently. They also recorded eye movements, and they have a chin EMG, which is pretty standard for the sleep studies. We don't have a chin EMG. I think we were talking about trying to find an EMG channel because that's important for detecting when people are in REM sleep.
That's right.
Is when the EMG, that's the muscle activity goes back. Okay. So please forgive my terrible animation thing here. This is Van Gogh missing one ear. But these are the electrodes that they chose, so all the ones that don't have X's through them are the electrodes that they're gonna use, but I just wanted to sort of show how it covers the head. So they don't have any frontal pole electrodes in their study, and they don't have any occipital. Or they don't really have behind the head electrodes. The F3 and F4 that I marked with stim, that's where they're injecting the current. And
Against the mastoids.
yeah,
So the mastoid is equally important. It's cathodal versus the anodal. And my guess is they ganged them together, so it was like one channel, and it was both anodal and then both mastoids.
it just said that they applied stimulation bilaterally.
Yep. Yeah, we'll have to look at it, but I bet their stimulator device only had one channel, and so it made both of these positive and both of these negative linked together. But we'll have to look at that carefully because we want to replicate this, for one of our conditions, even though we want to enhance slow waves with our own electrode choice, really with our WISP device. We want to emulate the WISP positions. So this is part of why it's important to know where the slow waves are and why I'm obsessing about the mapping of them in the temporal lobe, because, we want to make them stronger. But one of our conditions, we want to replicate this.
Yeah, so just to that point, for the study that we're going to do, we're partially replicating the study, so we're using these F3 and F4 electrodes, but we're testing that against another condition where we're stimulating temporal locations. So we're trying to see if one has an advantage over the other. So the declarative memory task, they had 46 semantically related noun pairs. And it said they were presented at a rate of one, is that one every 5 seconds? Or
Yeah.
1/5 of a second, okay.
I think 1/5 of a second would be pretty
Yeah.
fast.
Yeah.
Okay, and the interstimulus interval was 100 milliseconds. So they had 2 different lists that they used, so they got a different list each experimental session. Even though they were separated by a week, they didn't want to have any sort of learning effects over that period. So they had the pre-sleep paired associate learning, and that was tested with cube recall, so they would supply the first word for testing, and then you would generate the second word. And then, of course, that was in a different order than it was presented. They had unlimited time to recall, and then as soon as they answered, they were presented with the correct word. So if they got it wrong, they could have another chance to learn it. And then if they didn't get 60% correct responses, then the word pairs were presented again for learning and testing. And of course, a new order. So here are the results of the study for the declarative memory. So this is the difference in number of recalled words between what they recalled before they went to sleep and then what they recalled after sleep. So after sleep, they weren't given the list to study again, they were just tested. The increase was almost 5 words in the stimulation condition, and then, so in both conditions, their memory, their declarative memory improved. So that means that they actually remembered more words after sleeping than they did originally when they were tested, which is pretty remarkable. But the stimulation did significantly increase their memory.
And what was their total recall rate, or do you remember, out of the list of 46, how many did they typically recall?
So I have this, so this is just the
I see,
stats.
yeah. Yeah, so
um,
that's
they-
the increase there, is from the pre-sleep to the post-sleep, yeah.
Yeah, so they did still, they got about the same in pre-sleep in both conditions, but then they did have a higher increase in the stimulation condition. So, and the stimulation and sham conditions were, they put the electrodes on just the same, they just didn't turn the stimulator on, which is the same thing that we'll be doing for ours. Okay, so to reach the 60% criterion, that would be 27.6 words recalled, right? And so you saw, can you go back? So they obviously did a lot better than that. So I'm kind of wondering, how many times did they have to repeat the list to get to 60%? Like I wonder if most people did just automatically get that, because their memory performance was pretty good out of 46 pairs.
Yeah, it looks like they got right to it. If they're so good, it doesn't look like they had to repeat that much, or at least most people didn't.
Yeah, they didn't.
Otherwise, they would just get the criterion, 60%. It took them 2 or 3 times to get there, I would guess.
So then the big difference in our study is that we're going to be using unrelated words. So the word pairs won't have any semantic relationship. And so we're going to be pilot testing this soon to see how people do on this test, if they can reach 60% pretty easily, how long it takes.
What is remarkable in the 60%?
Just to replicate whatever they did. I don't know, we could choose a different, but I mean, it needs to be more than 50%, so I guess you could say.
Why not, if the set is significant, you have the pairs of words that are not related. Even
Yeah, well-
30-40% can be a good result.
Yeah, well, we're gonna do the pilot testing and we're gonna see what people get. And it might be, also, they were doing this 46 word pairs just all at once. And we were talking about where you're gonna use 40 word pairs and we're gonna break it up into lists of 20. So it could be that if they're only having to do 20 at a time, and then test, that maybe they do better. But basically we have to pilot to see what it's gonna be like. If 60% might not be realistic.
Yeah, I think that's it. Once we get a sense of how people do, we can make a choice. We want enough observations to have good metric properties. In other words, we want to have enough items that there is room for error both ways. We don't ceiling out or we don't hit the floor. So we're kind of guessing as to how to do it. But I don't think we need related pairs. I don't think there's any reason for that. There are different kinds of memory in the sleep literature. There's some evidence that creative remote associations are better after REM sleep. So relatedness and the meaningfulness of the material could be relevant, but here, I think for just simple declarative memory, we want the simplest test possible that still has measurement.
Will you guys be using like a standardized test like the WINS test or?
No, we're making up our own paired associates verbal learning test. We could use a standardized test, but there's not much of a reason to because we're not comparing it to norms.
Yeah.
So we don't really need the norms and we don't really need to pay for the standardized test, I don't think.
So can you go back to the slide where it was the change in performance or delayed recall? That with the graph. So it's like a difference between 2 more and 6 more, or 2 more and 5 more. What was the distribution look like for delayed recall for the stimulation group? The reason I ask is there a ceiling effect here? Like,
They
what was-
didn't provide that information.
They didn't.
Yeah.
What was the mean, I guess, for the stimulation group in the next line?
So it was,
41,
yeah, so it
44.
wasn't to 46, so they didn't remember all of them. I mean, I guess some people could have remembered all of them, and some people could
I
have.
would be aware of this, because depending on the distribution of performance in that group, that ceiling effect could have thrown things off. Because this group performed very well.
Yeah, so and another thing is that they said that, these people, a lot of the people who were in the study were med students, and so they said that they were really good at memorizing things. So maybe they maybe they would have been better off using non-related words for theirs because it was too easy for them.
Yeah. And what was the rationale for the 60% threshold, and if not, continue?
I think it was just to say that they learned it. Yeah, because they're not learning again when they wake up, they're just being tested again.
I just wonder because if they had to try several times, and that's overexposure compared to someone who performed well the first time, and then it'd be kind of difficult to account for that in your analysis.
Yep.
Yeah, well, so the 60% is 27 words, and so I don't think that they probably studied it a lot.
Got it, because they're all significantly higher in terms of.
Yeah.
Yeah, I think for our purposes, we do need to gain experience with this test and to see the range, but, U of O undergrads, they're not medical students, but they're pretty sharp by having gone to courses and they're still around, they didn't flunk out. So that will be different than a community sample that we might want to do, let's say with older adults from the community, who may forget where they parked their car. So we may need to have a wider range of test materials, but we got to start somewhere.
Yeah. Okay, so there was, I'm just gonna briefly talk about the procedural task results. They did have a motor procedural task where they did this. They tried to teach them these finger tapping sequences and seeing if they got them right in a limited amount of time. So we're not gonna be doing a procedural learning task for our study, but there were increases in the sham and stimulation conditions, so both conditions, but there was no significant difference. So the stimulation, the slow oscillation stimulation didn't increase their performance on the motor task, which is pretty in line with what we know about procedural memory. And then they did some additional control experiments. They had a nonverbal declarative memory, which was like pictures, and I think it was like picture matching, and then they had a neurotracing, which was another procedural memory task. And so in those experiments, the slow oscillation stimulation only enhanced the declarative memory, so it's just further proof that, or further evidence for that. Okay, sleep results. So, I don't know if you can read this. This is just this time spent in each sleep period. So they have sort of two different experiments here. There's one that you can see says theta stimulation. I guess they just took a subset of 4 people for that, and for that they stimulated at 5 hertz. And that was just sort of to compare, is it really the slow oscillations that are increasing the memory, and just have a comparison for a different kind of stimulation. And so the theta stimulation significantly decreased the slow wave sleep, which makes sense, right? If your slow waves are 4 hertz and under, and then you're driving somebody at 5 hertz, then it's gonna probably decrease that. So this just shows the time in minutes in each of the stages between stimulation and sham. For the slow oscillation, that was the 13 people, and then the theta was 5 people.
It's pretty interesting, actually. I mean, to me, it's kind of phenomenal that these electrical currents synchronize the brain.
Mm-hmm.
You know, they're kind of gross fields, electrical fields we're putting into the head, and yet the brain synchronizes its internal oscillations to go with them. It's almost too easy.
Yeah. Okay. Oh, and then I think Eustace mentioned that he thought it was strange they scored for 10-second intervals, and this is because this is the sleep stages during the 1-minute stimulation-free intervals. So this was the time between that 5-minute stimulation period. So that's what they're scoring. So they just scored each minute in 10-second intervals. Okay. And then they had supplemental materials, some pages of supplemental materials that I found. And this is different than the other chart. And I can't tell if this is like averaged over all the experiments they did or what, but it is a little different than the other chart as far as the time spent in each sleep. I guess probably because that's just a minute. So there was no significant differences between the stimulation and the sham conditions in the total amount of time spent in the different stages. So basically the power and the amplitude of their sleep was enhanced, but it's not like they got more sleep necessarily. And then they said that the 30-minute interval of stimulation and the corresponding interval were excluded from analysis of the entire night, so then you get a lower proportion of slow wave sleep that would typically be in that period. So that's why the slow wave sleep percentage is a little lower. They also found that inducing these slow waves increase the slow frontal spindle counts. So there's a difference between the frontal spindles and the parietal spindles. And so the frontal spindles are slower and the parietal spindles are faster. And so they found more of a relationship between these, the slow waves and the slow spindles. And they're stimulating the frontal area too. So they didn't find any significant differences between the stim and the sham for the fast parietal spindles. And then, might be kind of hard to see, but the panel on the left is panel A, shows the average power spectrum, and they just picked across the first 3 stim-free intervals. So remember there was 5 stimulation periods, and so they just picked the first 3. And so that's, the red is the stimulation and the black is the sham. So, and the gray bar is representing the frequency bands. So you can see in, let me see So this is the slow oscillatory band here, which is 0.5 to 1 hertz. And so the stimulation increased the amplitude. And then also this is the frontal spindles, the band from 8 to 12 hertz. And then this is the parietal faster spindles, the 12 to 15 hertz range. So it didn't really change. The stimulation didn't really change that much, but it still increased this low frequency band. And then
It did increase the slow spindles even in the parietal area. I'm not sure if that's significant, but
yeah, it wasn't significant. The increase in parietal spindles wasn't significant. Okay. And then panel B, so the panel on the right there, shows the stimulation-free intervals. So there's 5 stimulation-free intervals. That's the 1 minute between when the stim is off. And it was significant for the first 3 intervals that it increased the slow oscillations and slow spindle activity. And then you can see on the bottom right panel, there's no, I don't know, can you see the little stars that indicate that they're significant?
yeah,
We need like a bigger screen to really do this, but.
yeah.
Yeah, so then in the bottom right panel, there's no little stars there, there's no significance between the sham and stimulation. And so this paper showed that inducing slow oscillations in N2 sleep increased the slow waves and the slow frontal spindle density, and declarative memory was correspondingly enhanced. And then there's research indicating that I didn't really go into, that slow waves are driving the generation of the spindles. So it would make sense that they're increasing the slow waves, and that's increasing the spindles. And they also showed that the theta frequency stimulation decreased slow wave sleep, but it was non-significant decrease. And it also decreased the slow spindle activity. No, it was significantly decreased the slow wave sleep and non-significantly decreased the slow spindle activity, and it didn't enhance the memory. So then that's really showing further the relationship between the slow waves and the slow spindles and declarative memory. And so they indicated with this paper that inducing these slow potential oscillations has a causal role in sleep-associated consolidation of memory. So it's hard to see now because there's another image on top of there somehow. But this was from a paper called The Human Cortical Hippocampal Dialogue in Wake and Slow Wave Sleep. And it's just basically showing that you reverse directions in the transfer of the signals and information. So it's just showing basically how, like what Don was saying earlier, that your memories are in your hippocampus, and then they, when you sleep, they get sent out to the cortex. And so this is just showing that sort of transfer between wake and slow wave sleep.
Yeah, this would be really exciting. In fact, this Mitra paper might be a good one to review, because it would give us a mechanism for memory consolidation in sleep. I mean, how does it happen that you go to sleep and your memory gets better? I mean, it's kind of wondrous. And so the question is, what's really going on? And there are these hippocampal neocortical theories from mostly rat research, but to the extent that we could see them in humans and really characterize those mechanisms, that'd be really cool. So this might be a good topic for a future paper. I mean, I think, you know, at one level, we get these gross brain waves, and we could say what stage sleep you're in, but can we see the mechanisms? And that's what we really want. We want more insight into the focal activity of different brain areas.
And there was also a paper that I think if we're gonna keep doing these sleep and memory things, we should probably talk about, was it Norimoto? Can't remember. I've been reading a lot of sleep and memory papers, so I'm not sure, but there was one that showed, like you were saying with the rats, and they were silencing the hippocampal sharp wave ripples,
Yep.
and then that decreased the rat's memory for the maze or whatever they were doing. And so if we're saying that the slow waves are sort of driving the spindles, and then the spindles are in turn driving the hippocampal sharp wave ripples, then maybe what we're looking at with the slow wave sleep is just like the beginning of that, you know, step one in the cycle, but what really is important is the sharp wave ripples,
Yep.
which we can't see with the EEG.
Pretty sure we won't be able to see anything in the hippocampus, actually. But the nearby cortex, the entorhinal cortex and the subiculum, these are medial temporal cortical areas, that we might see activity there. Now, it wouldn't be the sharp waves, because those are really unique to the hippocampal formation itself. But that would be the exciting thing here, is if we could look into those mechanisms and see how specific they are. One of the findings of the Tononi lab that I didn't mention was that if you have a practice or a memory load of a certain brain area, that area will show more slow waves while you sleep. So they did a pursuit rotor task that engages the right parietal area. And then when they went to sleep, that right parietal area was having more slow waves. So that's a really specific kind of a model. It's not like the whole brain is doing something, it's really focal. So a mechanism like this would be really cool if we can separate it.
Yeah, and obviously we're gonna have a lot more electrodes in our study, so we'll get to see a lot more effects, and then we're gonna be stimulating the temporal region also, so it should be interesting to see what we find in our study.
Are you guys gonna shoot to match that, was it 0.537 current density on milliamps per centimeter squared, or do you have something else in mind?
I don't know. I think, yeah, I'm not that up on the technical specs, but, I know we're gonna use F3 and F4, but then we haven't decided what we're gonna do for the temporal.
Right.
Were you planning on doing multiple electrodes for that, or?
Probably, just so you can use the G10 system and get the current cranked up. So my thought was to use a bunch of electrodes. But when I planned it, in fact, when I wrote the grant, I was using the Murphy paper to map the frontal areas. And I wasn't careful enough to see that they were throwing out the electrodes on the neck. And that could be a big mistake. They may have mislocalized, you know, saying it was frontal, when maybe these slow waves are mostly temporal lobe, which could change our whole strategy. Maybe we should be doing like a mastoid to, you know, frontal, or mastoid to cheek, or I don't know how to do it. But the good thing is with the GeoSource software or with Sorcerer, we can model where the current goes. So if we map the slow waves accurately with a complete electrode array, that should teach us how to enhance them more effectively. On the other hand, maybe it doesn't matter. Maybe you can zap the brain anywhere and it still synchronizes. So there's a lot to figure out, I think, with that.
Yeah, and they only stimulated F3 and F4, so.
Yep.
Any questions about anything?
I may have missed it, but are these subjects serving as their own controls? I forget the study design.
Yeah,
They are, okay.
yeah, so they were,
Two different things.
Yeah.
Yep, they had sham and stimulation.
Yeah,
within
it was a week apart. And then they took, there was a lot of experiments that they did as controls. There was a lot of other control things that they did, like testing their cortisol and doing mood assessments and state assessments. They did like the PANIS and all these things to make sure that their mood and alertness and sort of all their parameters were even. They had a lot of controls for this, but I didn't really go into them. But yeah,
And I'm assuming it's counterbalanced, so half had stem first, half had sham first.
yeah. Yeah, the order of the list, or the list, whether it was in sham or stem, and also which session it was. The thing I don't know, that I mentioned before, is whether they had a second habituation night. Like if it was just like, they had one habituation night and then they had stem or sham, or if a week later, did they get another habituation? And, you know, it's counterbalanced, so that would sort of take care of it, but they did only have 13 people, so it would be interesting to see if that had an effect.
Right.
You know, and we were talking about doing one habituation night and then the next night doing the stem, so, or the stem or sham.
And we don't know if they had a habituation night. They didn't say, so they probably didn't.
Well, they had at least one habituation night. I don't know if when they came back for the second
I see,
session, if they had a habituation night before that.
I see.
So there was like
So probably not.
habituation night and then stem or sham, and then like a week later stem or sham.
Yeah, yeah. Well, that would still help with the first night issues. The first night in the lab is weird.
Yeah.
So, yeah. And that's our design, right? But we're gonna do them sequentially, not a week apart.
Well, so, yeah, I mean, we had talked about different plans for that, but the basic plan is that there's 4 nights of sleep for the study that we're doing. And so there's going to be the one night first night that they know is just sleep mapping. And then there's 3 more nights where it's frontal stim, temporal stim, or sham. And so of those 3 nights, they don't know which is which.
Right. I think
That's a superior design than this, because that week in between without a set habituation night could definitely affect the results, I would think.
Yeah, we did though, we weren't sure whether people would want to come and agree to sleep in our lab for 4 days in a row. So we talked about doing, having them come 2 nights and then having them come another 2 nights. But yeah, we'll have to talk about that more, I'm sure, to figure out what's the best idea.
Well, that's right. I think we can see what people are willing to do and try to adapt the design to it. But the 4 nights, I think, sounds the best to me if we're able to do that and get people engaged for it. But, you know, running a sleep lab is new stuff. I've never done it before. None of us have done it, so we have to find out. But my hope is that we extend this to the Parkinson's work. I mean, we want to do vibrotactile during sleep for one of our new pilots, and we want to do electrical neuromodulation of Parkinson's and try to disrupt their oscillations. Sleep would be best if we could make it work then, because then they could go home and have this be a thing they do during sleep, and they wouldn't have to wear silly gloves all the time. They could either wear it during sleep, or we could do electrical brain modulation in sleep. So I think it's really our job to become sleep scientists, to figure it out. Well, that's a nice job here, Megan. That helps to get us all refreshed. Any other questions with it? Or any general questions? Yes?
I still have a question about the epilepsy you were talking about earlier.
Yes.
So in their EEG, there is a mild abnormality at first, and then it went back to normal.
Yes.
What happened with it, like after they went back to normal, like between the mild abnormality and the big positive discharges? What happened in between?
Oh, and the one that I showed, well, what I showed was they had a little spike wave discharge, and then it was somewhat normal, and then the whole series of spike waves. That was just one patient. And you see a lot of stuff. A lot of times you'll see spikes in a normal person's EEG, and we don't know what it means. There's some evidence that the more spikes you have, the worse your cognition is in kids. But, you know, it's hard to say what the significance of it is. I think your brain is not functioning very well when you're having epileptic discharges.
So not everyone has like this normal phase in between, right?
Yeah, it looks like when the EEG is normal, your cognition's pretty normal. But we know after a limbic seizure, after a more generalized seizure, the brain is not in such good shape. It takes a while for the person to recover. But that's why the absence seizures are so interesting. They have those spike waves, and then they're pretty normal as soon as they're done. So it's kind of a remarkable clue. And we do know that the spike wave seizures, those 2.5 cycles per second, big waves and then spike, big waves and then spike, we know that those involve a circuit of the frontal pole, particularly, because that's where we find the spikes we're engaging, and the frontal BA10 modulation of the reticular nucleus of the thalamus. I had a picture there. It's a sheet of GABAergic neurons that surrounds the thalamus, which is kind of the control center of a lot of the brain activity. And that regulates the thalamocortical projections back to the cortex. So we know that cycle. It's been described in animals pretty well. And somehow that cycle seems to relate to these normal sleep oscillations. So it's like a clue that something about the thalamus and the cortex regulating the sleep cycle with the hypothalamus, the brainstem. I mean, there's a whole set of circuits that are involved, but there's something about that gets disrupted in these absence seizures, but it also is active in normal sleep. And it's somehow helping us to consolidate memory. So it's a really fascinating area of science where we should know this. You know, if we're going to have brains and use them every day, we should know how they work. We should have an operating manual. And yet you go to the university and nobody gives you the operating manual for your brain. And we don't even know that these things happen. So using our tools to figure them out is pretty important, I think.